Picture this. It is November 2024. You're looking at Mount Fuji, Japan's most iconic peak, right?
Right, the classic image.
Yeah, exactly. Usually by this time of year, it is capped in this brilliant, pristine white snow. But instead, you're looking at bare, dark rock.
Just completely exposed.
Completely exposed, yeah.
Deep into the autumn. Welcome to today's deep dive. I'm your host, and I'm here with our expert to unpack something that honestly blew my mind.
Thanks for having me. And yeah, that image of Fuji is jarring. It's actually historically significant.
Because it was the latest, right? Yeah, the most delayed first snowfall on record since they started keeping track back in the 1890s.
Which is wild. And that bare mountain isn't just some geographical anomaly. I mean, it is the physical reality of our near-term climate. But while the mountain sits bare out on the oceans, the global shipping industry claims they are rapidly fixing this problem.
Right, with their miracle fuel.
Exactly. This miracle bridge fuel called LNG, or Liquefied Natural Gas. Today we're diving into a fascinating piece from the Deep Draft. It's written by Captain Raghu Sharma, and we're looking at why that supposed miracle might actually be, well, a massive mathematical illusion.
It is an incredibly timely analysis, too. We often look at the maritime industry as this slow-moving monolith,
Like big ships, slow changes.
Exactly. But they are under massive pressure to decarbonize right now. And their chosen method for doing that, this big pivot to LNG, it reveals a huge blind spot in how international regulators actually measure environmental progress.
So let's get right into the mindset of the industry. Because to understand the illusion, I feel like you have to understand the allure, right?
Oh, absolutely.
On the surface, if you're a mariner standing on the deck of a newly retrofitted ship, LNG feels like a massive leap into the future.
It really is a sensory shift. To understand why ship owners fell in love with LNG, you have to look at what it replaced.
Which is heavy fuel oil.
Right. Traditional marine heavy fuel oil, it is literally the bottom of the barrel. It's thick, viscous, dirty stuff.
Gross.
Yeah, and when you burn it, you get black smoke, you get soot covering the deck, and you get these crazy high sulfur emissions. The pollution is visceral. I mean, it coats the air.
But then you fire up an LNG engine, and it's totally different.
Night and day. The black smoke vanishes.
There's no soot at all. The engine stacks are significantly quieter, too. You look up at the funnel, and it just feels pristine.
You're seeing a 20 to 25% reduction in visible carbon dioxide coming out of that stack, and it easily clears all the international sulfur caps.
Plus, practically speaking, the engineering of these new vessels gives the industry a huge safety net, right?
Yeah, because most of the ships adopting LNG are built with dual fuel engines.
Meaning they can switch back if they need to.
Exactly. They're designed to run primarily on gas, but the plumbing is still there to burn marine diesel or heavy oil if they absolutely have to.
But reading through Captain Sharma's breakdown, the whole setup feels a bit like a sleight of hand. I mean, to me, it's like switching from smoking unfiltered cigarettes to vaping.
That is a perfect analogy.
Right. You switch to a vape, it smells like a artificial cherry or whatever. There's no visible ash falling on your shirt, and you feel like you've completely solved your health problem.
You look clean.
You look totally clean. But the critical question isn't about the ash you aren't producing. It's about what you are actually exhaling into your lungs.
And that question completely unravels the clean stack narrative. Because when a ship burns LNG, the invisible exhaust isn't just a slightly reduced stream of CO2.
What are they exhaling?
Methane. Primarily methane. And the moment we look at the thermodynamic and chemical reality of methane, the whole bridge fuel concept just collapses.
So let's talk about the math regulators use, because I know scientists measure these greenhouse gases using global warming potential, or GWP, and carbon dioxide is the baseline.
Right. CO2 is the standard unit of measurement.
But the source material highlights this massive discrepancy in the timeline used for this math. Why does the timeline matter so much when we evaluate methane?
Because gases don't just sit in the atmosphere forever, they degrade at completely different rates. Methane is a highly unstable, fast-acting gas.
Okay.
So if you evaluate it over a 100-year timeline, which scientists call GWP 100, it absorbs roughly 30 times more thermal radiation than carbon dioxide.
Which is already terrible. 30 times is a lot.
It is terrible.
Yeah.
But because methane breaks down relatively quickly, stretching the math over a century essentially dilutes its initial violent impact.
Right. It flattens the curve of the damage, so you're spreading out the spike.
Precisely. If you look at methane over a 20-year timeline, which is GWP 20, it is a staggering 80 times more potent than carbon dioxide at trapping heat.
Wait, 80 times.
80 times.
If climate scientists have known for years that methane is 80 times worse in the short term, how did a trillion-dollar maritime industry convince international regulators to let them use the 100-year metric? Did they just ignore the 20-year reality?
It's a classic policy compromise. Policymakers and industry regulators overwhelmingly prefer the 100-year metric in their spreadsheets.
Because the math looks gentler.
Exactly. It allows massive, expensive fossil fuel infrastructure to remain viable on paper for decades longer. If regulators used the 20-year metric, the pivot to LNG would literally be dead on arrival.
But the atmosphere doesn't care about our policy compromises.
No, it doesn't read spreadsheets.
The atmosphere doesn't average out thermal trapping over a century just to protect stranded assets. The next 2 decades are going to dictate the actual weather you and I experience.
Right, the physical reality.
The severity of the storms, the drought cycles, the bare slopes of Mount Fuji, that is all governed by near-term 20-year warming.
Which means physical measurement is the only language that matters here. If methane is 80 times worse than CO2 in our current window, the critical engineering question becomes how much of this unburned fuel is actually escaping from these supposedly clean ships?
Let's dig into the mechanics of that. Because ships aren't just venting gas into the sky for fun, they're trying to burn it for propulsion.
Right, it's their fuel.
So why is so much of it escaping?
It comes down to a phenomenon called methane slip. And it's an inherent flaw in the low-pressure, dual-fuel engines that dominate the current fleet.
Okay, how so?
Methane has a notoriously high auto-ignition temperature. It takes a lot of heat to guarantee combustion.
So what happens inside the cylinder when it fires?
Well, in a massive marine engine, the temperature inside the combustion chamber isn't perfectly uniform. There are microscopic crevices or these little pockets of cooler air near the cylinder walls. So when the spark fires, the flame front sweeps through the chamber, but it misses those cooler pockets.
So the gas just hides there.
Exactly. That raw, unburned methane survives the combustion stroke, slips straight past the exhaust valves, and is flushed out the funnel into the atmosphere.
But picture it like an old gas stove in a kitchen. You turn the dial, but you turn it a little too slowly, right?
Yes.
You hear the hiss, you smell the gas flooding into the room, and it takes a couple of seconds before the spark finally catches. Ships are effectively doing that on a massive industrial scale.
That is a brilliant way to visualize it. And the stove analogy holds up perfectly when we look at how ships actually operate.
What do you mean?
When a massive vessel is running at low, say, carefully maneuvering through a port, or slow steaming to save fuel, the engine isn't roaring at peak heat.
So the internal cylinder temperatures drop.
Right. And during those specific low-load operations, methane slip drastically increases. The flame front is weaker, and the gas just escapes.
And for years, the industry just modeled this slip theoretically, right? They just assumed it was a negligible percentage.
They did, yeah.
But Captain Sharma's piece highlights a 2024 international study called the FUMES campaign. And researchers finally decided to stop assuming and start measuring.
Yes, the FUMES campaign. It is a watershed moment for maritime data. Researchers actively measured the exhaust plumes from 18 different LNG-fueled ships.
Out in the real world.
Operating out on the water under completely normal conditions.
And the data completely shatters the theoretical models, doesn't it?
Completely. They found an average methane slip of 6.4%.
6.4%.
Which is nearly double what the official regulatory bodies assume in their compliance models.
Wow.
The industry was operating under the assumption that these engines were achieving a near-perfect burn, and the physical reality is that they are bleeding pure methane.
The way the industry handles this accounting is just, it's wild to me. It's exactly like someone who decides they're going on a strict diet.
Oh, here we go.
They weigh all their food, they track every single calorie on their app from Monday to Friday. But then on Saturday and Sunday, they eat 3 pizzas, drink a case of beer, and entirely ignore the app.
Naturally.
Then they step on the scale on Monday, look at their weekday spreadsheet, and declare, my diet is a massive success.
It's selective accounting. They are rigorously counting the 20% reduction in visible carbon dioxide at the stack while completely ignoring the invisible methane binges happening every time the engine misfires, maneuvers, or runs at a low load.
But here's the crazy part. Even if that marine engine burned at 100% efficiency and 0 methane slipped out the stack, this fuel would still be an atmospheric disaster.
Because of the supply chain.
Exactly. The funnel is just the end of a very long, very leaky global pipeline. To really understand the cost of LNG, we have to look at the thermodynamics of how it gets onto the ship in the first place.
This is where the term hidden life becomes crucial. Natural gas does not come out of the earth as a convenient liquid.
No, it's a gas.
Right. To compress it enough to fit into a ship's cargo tanks, you have to subject it to a violently unnatural state. You have to cool it down to negative 160 degrees Celsius.
Wait, negative 160? From a pure physics standpoint, you don't get something to negative 160 degrees just by tossing it in an industrial freezer.
Not at all.
What is the actual energy cost of forcing gas into a liquid state?
It is astronomical. Liquefaction plants require massive, sprawling trains of compressors. And to power those compressors, the plants usually burn a huge portion of the very gas they are trying to cool.
They burn the gas to cool the gas.
Exactly. Modern facilities consume roughly 7 to 15% of the total feed gas just to run their own cooling systems. We are talking about 300 kilowatt hours of electricity consumed for every single ton of LNG produced.
So before the fuel even leaves the dock, before the ship has moved a single inch, you have already cannibalized up to 15% of your product.
Yep.
And created a massive carbon footprint just to make the fuel small enough to physically transport.
Exactly. And the thermodynamic battle doesn't end at the dock. Once that supercooled liquid is pumped into the ship's insulated tanks, the vessel sets sail across warm oceans.
And it warms up.
Right. No matter how advanced the insulation is, heat penetrates the hull. The liquid inevitably begins to warm up and evaporate back into a gas. In the industry, they call this boil-off.
How much are we losing during a standard voyage to boil off?
Even on the most modern LNG carriers, they lose about 0.1 to 0.15% of their total cargo every single day to natural evaporation.
Every single day.
Yeah. Now, modern ships try to capture some of that boil-off gas and route it back into the engines to burn as fuel, but the system is never perfectly closed. A fraction of that boil-off inevitably escapes into the atmosphere as pure, unburned methane.
And we still haven't even traced this back to the wellhead.
We haven't.
I mean, if the ship is bleeding methane and the ocean transport is bleeding methane, what does the extraction process look like? Because gas extraction is notoriously dirty.
This brings us to the geopolitical reality of the upstream supply chain. The International Energy Agency releases an annual methane tracker report, and the 2025 data paints a very fractured picture.
How so?
Well, if your LNG comes from places like Norway, the extraction is highly regulated. The infrastructure is modern, tight, and relatively clean.
But shipping is a global market. You don't always get Norwegian gas.
Far from it. If you look at gas extracted from older fields in Russia or parts of Central Asia, the infrastructure is basically a sieve.
A sieve.
Yeah. Methane escapes during the initial drilling. It leaks from thousands of aging wellheads. It vents from hundreds of miles of gathering pipelines, and it blasts out of poorly maintained compressor stations.
Wow.
So when a shipping conglomerate claims their LNG is a quote-unquote clean alternative, they are banking on a massive, unverified assumption about where that gas originated and how tightly the pipes were screwed together thousands of miles away.
This is the exact section of the source material that genuinely stopped me in my tracks.
Yeah.
Because there is a 2023 study from Cornell University that refused to let the industry segment its accounting.
They looked at the whole picture.
The entire life cycle. They added up the upstream extraction leaks. They added the massive thermodynamic cost of cooling it to negative 160 degrees.
Right.
They calculated the boil-off during oceanic transport, and they factored in the methane slip at the ship's engine. And crucially, they evaluated all of this on the 20-year timeline, the GWP-20 metric that dictates our near-term weather.
It's the most honest accounting of the fuel's life cycle to date, really, and the conclusion is just brutal.
When you add all those invisible leaks and energy costs together, the Cornell study found that LNG can actually have a 33% higher climate impact than coal.
Than coal. Let that sink in.
Coal, the literal poster child for 19th century soot-choking pollution. On a 20-year timeline, this multi-billion-dollar cutting-edge bridge fuel can be mathematically worse for the atmosphere than burning rocks.
It is a profound indictment of partial equations. I mean, it demonstrates exactly what happens when policy outpaces physics. We replaced highly visible black soot with an invisible, hyperpotent greenhouse gas.
And patted ourselves on the back.
Because our regulatory spreadsheets averaged the disaster over a century.
Okay, hearing all this, I am genuinely starting to panic a little bit. If the infrastructure is already built and these ships have a lifespan of 20 to 30 years, are we just permanently locked into this failing bridge fuel?
Well, not necessarily.
Is there any technological fix to plug the leaks?
There is a way out. And it relies on some incredible heavy-duty engineering. We are seeing a real breakthrough emerging from Japan right now.
Okay, good. We need some good news.
The reality is LNG ships are on the water. We can't sink them. But if we can retrofit the existing fleet to actually neutralize the slip, we can make a massive dent in the near-term warming.
So let's look at the fix. Because in 2025, a coalition of major Japanese maritime and engineering companies, Mitsui O.S.K. Lines, Yanmar Power Solutions, and Canadivia Corporation, they teamed up to test something called a methane oxidation catalyst.
Right.
And they actually installed this system on a massive, working, LNG-fueled bulk carrier called the Raimai.
The mechanics of the Raimai test are fascinating. They essentially built an advanced chemical filtration system for the exhaust. It uses a process called exhaust gas recirculation, or EGR, combined with a specialized catalyst bed.
Okay, so how does that actually intercept the methane slip we talked about earlier?
Yeah.
The gas hiding in the cold pockets.
Right. Remember those microscopic pockets of unburned methane that escape the combustion chamber?
Yeah.
Instead of letting that exhaust blast straight up the funnel, the EGR system captures it and routes it through this dense chemical catalyst. The catalyst lowers the activation energy required to ignite the gas.
Oh, I see.
So even though the exhaust isn't blazing hot anymore, the chemical reaction forces that unburned methane to finally oxidize. It breaks the CH4 apart and converts it into carbon dioxide and water vapor before it can hit the open atmosphere.
Wait, it intentionally turns the methane into CO2.
Yes!
We spent all this time trying to reduce CO2. Why is creating more of it a victory?
It's all about that GWP trade-off. Remember, over 20 years, methane is 80 times more destructive than CO2.
Oh!
If you use a catalyst to catch a molecule of methane and chemically downgrade it into a molecule of CO2, you have just drastically reduced the overall thermal trapping potential of that exhaust plume.
It's damage control at the molecular level.
Exactly.
Ah, that makes total sense. You're taking an 80x multiplier and dropping it down to a 1x multiplier.
On.
And the sea trials on the Raimai proved it works in the real world. They achieved a 98% reduction in methane slip.
98%.
98%. That essentially plugs the gaping hole in the ship's exhaust.
Technologically, it is a massive triumph. But this brings us to the ultimate frustrating irony of the maritime industry.
Okay.
Even with this incredible technology proven and available, there is a massive regulatory roadblock preventing ship owners from adopting it.
Well, of course there is.
The international frameworks, specifically the IMO measures and the European Union's FuelEU maritime regulations, are inherently flawed.
Let me guess.
Yeah.
Because they are still hyper-focused on the 100-year metric.
Partially, yes, but primarily because the rules were originally written strictly to measure carbon dioxide at the exhaust pipe.
Seriously.
Yeah. The regulatory bodies completely ignore the upstream supply chain leaks, and they lack the strict mechanisms to properly penalize unburned methane slip.
So if I'm a ship owner, I look at the international rules. I see that burning standard LNG keeps me legally compliant because it lowers my visible CO2 by 20%.
Right.
And I ask myself, why on earth would I spend millions of dollars retrofitting my ships with a Japanese catalyst if the law doesn't force me to?
Exactly. The regulations are rewarding the illusion of compliance rather than actual atmospheric reduction.
So what does this all mean for the future of the industry? I mean, it seems like we have the engineering to patch the leaks, but our accounting system is so fundamentally broken that it actively discourages the people who want to fix the problem.
Exact words.
We are settling for what looks clean instead of what actually is clean.
That is the crux of the issue. The ultimate destination on the other side of this transition cannot be LNG. It has to be genuine, zero-emission fuels.
Like what?
The industry needs to rapidly scale green methanol, green ammonia, and hydrogen, fuels that do not rely on extracting carbon or methane from the earth whatsoever.
But getting there requires capital.
Exactly, and we will never direct the capital to the right solutions until we are ruthlessly honest about the bridge we are currently standing on.
That perfectly synthesizes everything we've unpacked today. You, the listener, now know the critical difference between what is visibly clean to the human eye and what is chemically clean to the atmosphere.
It's a huge difference.
We started with the mariner, standing on the deck, looking at a smoke-free exhaust stack and feeling a sense of progress. But true progress doesn't come from simply making the smoke invisible.
No, it doesn't.
It comes from tracking every single molecule, honestly, from the wellhead to the wake.
Because the atmosphere, as Captain Sharma brilliantly notes in the piece, does not read our policy documents. It doesn't care about our 100-year averages, or our stranded assets, or the thermodynamic cost of freezing gas to negative 160 degrees. It only reacts to what is physically released into it.
The actual molecules.
Yes. When we rely on clever accounting tricks to hide a 20-year disaster, we are only lying to ourselves.
Which brings us back to that striking image of Mount Fuji. Bare, dark, and exposed in the late autumn. It's a heavy visual, but the author leaves us with a vital reminder.
Nature's resilience.
Exactly. Eventually, the winter did arrive. Mount Fuji took back its snow. It stands white and calm above the bay again. The Earth's systems do have this incredible, resilient capacity to rebalance and renew themselves.
They do.
But that renewal isn't guaranteed. It requires us to correct our course. And we can only correct our course if we govern our industries with uncompromised, honest data.
We have to measure everything, assume nothing, and never mistake a clear exhaust pipe for a healed planet.
So, we want to leave you with a final thought today. Something to mull over long after this deep dive ends. The next time you click buy and order a package online, take a second to consider the hidden atmospheric ledger of its journey across the ocean.
It's a long journey.
It really is. And if our most celebrated, multi-billion-dollar green solutions in global shipping are heavily reliant on invisible leaks and clever accounting tricks, what other invisible debts are we unknowingly accumulating in our daily lives that will suddenly come due in the next 20 years?
It's a question we all need to start asking.
Thank you so much for joining us on this deep dive. Keep questioning the world around you, keep looking past the visible smoke, and we will catch you next time.